Well, hi, good morning. Thank you for coming and keeping me company here in my shop while I work on this radio. Today is March 9th, 2024. Rainy day outside. It's going to rain all day long, apparently. So, some interesting things have come up here in the radio. One of them is not so interesting, the antenna wire connected to a switch here. This is the band switch. I was thinking about this a little bit. It's probably just directing the antenna to different coil windings on the antenna coil. We'll see it on the schematic eventually, but that's probably all that is. Nothing more than that. So it's just kind of broadcast or shortwave. Two settings there. These capacitors are replacements for the original. These might be just fine. These two here I'm talking about. Or they might not be fine. I'm not really sure. When these were done, they could have been done 25, 30 years ago. These don't look like very, very modern capacitors. They're still pretty large in that. So I'm thinking about changing these, but I don't think it's critical at this point. There is another safety concern here in this radio, like all these radios, and that would be this capacitor here. So this capacitor is connecting the chassis right to the power line here. And its purpose is to prevent radio type signals from coming into the radio along the power line and radio type signals from going out on the power line to affect other radios and whatnot. The problem with this guy is if he should short out, and I'm not exactly sure what would happen in this radio, but or if this is extremely leaky, this could make the radio dangerous in terms of the chassis. Again, we need to look at the schematic a little bit and just spot this on the schematic and confirm what's going on. I mean, there's lots of things soldered to the chassis in this radio, aren't there? Aren't there? Aren't there? How the radios, how the engineers design the radio in terms of the chassis is an important thing to get a grip on early on when you're doing this kind of work. This is kind of radio's relatively safe because it has a big power transformer and the circuitry is such that it's not likely to have any kind of shock hazard on the chassis. The smaller radios, the little tabletop 1950s radios with 5 tubes in them, sometimes 6 tubes, sometimes 4, and no power transformer, no big, power transformer. Can you see it there? Can't really see it there. No big power transformer. Okay, I'm not going to show it to you. Those radios are very dangerous, and you need to understand what you're doing with them. These big ones, you might kind of counterintuitive. You think bigger radio, bigger dangers, but not really. Okay, the next thing is the motorboating. What I believe is automatic volume control affected motorboating type problem in here. Almost certainly due to a bad capacitor or a weak capacitor somewhere. I think I'd like to try to guess which capacitor that is and then start replacing them in the order of my guess, because my guess is my first guess won't be right, but I'll start taking guesses. It's got to be this guy because of these reasons, then we'll change it and see if the motorboating does go away or not. What else is there in here? So I think really I need to replace this right off the bat. But let's look on the schematic. Just see this on the schematic. And yeah. Here I've just got to find at least one more soldered connection to the chassis. Here's one, and it's connected right up onto a pin of one of the tubes. So probably every tube has a pin soldered to the chassis, and that's one leg of the heaters on the tubes. They're probably all being fed through the chassis, essentially. The chassis is a conductor. Let's look at the schematic here. Okay, let's have a look at the schematic here. So, first time looking at this schematic, I think an overview would be useful. There's the model number 5542. Alignment is on another page. This is a parts list here. All this. Let's just look for some notes. Any special notes? Input, plug and cord. AC switch on volume control. Phono switch and motor. So they're showing how the a record player would fit into this. It's dotted in case it doesn't exist. Okay, we have a light. Is there just one light in this radio? Yeah, one light bulb. There it is there. So there's the voltage, 255. I think I measured, here's 270 here. I think I measured, did they have a voltage up here? 205. I think I was measuring a little more than that. Okay. So the reason I'm looking at this schematic, the specific reason, is to find the capacitor that connects to the chassis and consider it. Now, where is it? That would be it right there. So if you look, you'll see here's the plug that's going to go on the wall. Here's the wires coming from the plug. Here's the switch, the on-off switch. And then the wires, just ignore this dotted. In fact, this doesn't exist, right? The record player doesn't exist in this. So just ignore the dotted lines. The line comes along, goes through the primary side or primary winding of the big transformer and comes out again and leaves. So the hydropower, as we like to call it here in Ontario, is only put here. Everything else that's being driven by electricity up here in the radio is getting its electricity from this side of the transformer. This means there's a complete isolation of the 120 volts from the rest of the radio. It's an isolation transformer operating here, and that's part of why you might be a little more safe working on this kind of radio than working on one that doesn't have a big transformer in it, those 5-tube danger radios. Now what I'm referring to there is something called the hot chassis problem. And if you literally type that into Google, hot chassis problem, or maybe radio hot chassis problem, you'll be reading up on what I'm talking about. And if you are working on radios, and you do work on those 5-tube radios, and you're listening to me and going, what's he talking about? You better learn this stuff. You better learn about the hot chassis problem. But not a problem with this kind of radio, so I won't dwell on it. So what's this capacitor for? So this symbol here, which is kind of poorly drawn, it's the same as this symbol here, right here. Kind of a downward arrow. This might be one also here. I'm not sure what that is otherwise. Here's one here also. These are all connections to the chassis. So if we go through, now earlier I thought I convinced myself that the heaters were fed through the chassis, one side, but that's not the case, because you see here's a heater, and there's a little arrow there, a little arrow there, and that's just indicating this goes off and connects to these little arrows here. So just a bunch of wires they didn't want to put on the schematic here, it'd be so hard to look at. But neither of these are connected to the chassis, but I saw something soldered to the chassis. And there you can see, there's the symbol for solder to the chassis in this case, right there. And there's another one there, another one there. Notice it's always on pin 1 of the vacuum tube. Pin 1, pin 1. And here's one also, pin 1. So the vacuum tubes in this radio, he just got quiet. The vacuum tubes in this radio are glass tubes. All of them. All of them? What about the very first one? Yes, they're all glass tubes. Okay, so this connection is about shielding the tube. Now, you heard me saying glass tubes because I thought, well, if they make this connection here, this must be a metal-clad tube. Very common when you get up into 1945, you know, and up in that range. Not in this radio though, they're all glass. So exactly what's going on here with this connection, I'm actually not sure. Now one of the tubes has a metal shield on it. I'm just looking at it now. That the way it's connected to the chassis is just through physical mechanical connections of the actual metal sleeve, and I wouldn't be surprised if it's this tube here. Of the metal shield that's on the outside of the tube. It's just mounted on the chassis, so that's how it gets its connection. So I don't know what this is, but I saw something soldered in there. You notice there's a little voltage number here, 6.2, 6.2. Very hard to read. This is added in after. All these 90 volts, all this stuff. So I had a draftsperson draw this up. And you can see the draftsperson's style of writing. It's right here. It's nice. It's not bad at all. Nice and flat on the bottom, you know, straight across, all that kind of stuff. But then you see these 6.2, 90 volt. That's been penned in afterwards. Somebody penned that in afterwards. That's my opinion. Does it matter? Not one bit. Why am I telling you? Because my mouth keeps opening and words come out. And that's basically why. So I want to replace this. If this guy is leaky, then this connection to the chassis will start energizing the chassis. The plug here is not polarized, which means you can stick it in the outlet this way or that way. If you stick it this way, then you might have the grounded side coming up here, and not a problem. If you stuck it in the other way, it's a 50-50 chance, of course. You could have the 120 volt side coming up here and the leaky capacitor right onto the chassis. Now, I still think the chassis is intimate in here. You can see the chassis connection there, chassis connection here. So there's lots of things all connected to the chassis out here. All kinds of stuff. All kinds of stuff is connected to the chassis. So, okay. This is still the singular connection to the chassis from the plug. Everything else is on this side, on the isolated side. So this capacitor, if this were shorted right out, well, I don't know what would happen, to be honest with you. I think things would happen. But one of the things that would happen is the chassis would become dangerous. So we don't want that to happen. So I'm going to replace this capacitor after all that talk. And the reason I'm dwelling here looking at this is because I'm just letting all this stuff sink into my head here. Like, what is this? This again is showing dotted lines. Oh, phono pickup. They wrote it right there. Phono pickup. So this is how they're showing where the phono is connected. Phono pickup. So the radios, I don't want to get into this in detail yet. The radios is here. This is the radio, and this is the audio amplifier on this side. And right in between is the volume control and a few circuits. So if you want to feed an audio signal into the amplifier, you got to feed it into this area here somewhere, and they're feeding it right here, right into the top of the volume control. And also coming into the top of the volume control is the output of the radio circuit right here. Okay, I don't want to go, like I said, I don't want to get into this in too much detail. Eventually I will go through this from front to back, but not right now. Right now I'm anxious to get rid of the motorboating problem. So when we think about the motorboating problem, we want to look for a big important capacitor that is on the screen circuits. That'd be my first guess. The screen circuits are not being quieted. So here's a screen circuit, this grid. We'll just follow it back. And we're going to look all over the place for a large capacitor, probably going to the chassis. See one. Oh, C13 to the chassis. So this guy is probably the guy who's in charge of stopping feedback from coming out of the circuitry here. Strong signals coming out here. And if they're allowed, they will work their way back and find their way to a signal grid and start coming through again, re-amplified. And that's how you get an oscillation going. And that's why the motorboating is happening. Now let's look at the motorboating question also. Motorboating indicates that the automatic volume control circuit is involved in what's happening to the radio. The automatic volume control has a capacitor on it which slows its reaction rate to variations in the signal coming in on the antenna. If you think about it, normally you tune one of these radios in and the signal is constant, and this thing I'm talking about, automatic volume control, will throttle the volume to a certain level. It all happens as you turn the volume control, you don't even know it, and it'll all be stable. But if you did have a signal getting stronger and getting weaker and getting stronger and getting weaker, fading in and out, the radio is automatically adjusting itself. It's turning up its sensitivity and turning it back down. So what comes out of the speaker is fairly even. The real purpose, though, is when you tune through stations. You tune a weak station and you tune a strong station. The radio is designed to make them both come out at about the same volume out of the speaker. So now here's the truth. When you tune between stations with these radios, and this is true of radios all the way from the mid-1930s all the way up to now, pretty well. When you tune between stations, there's no signal derived here to reduce the sensitivity of the radio. Right? Strong signal, radio turns itself down. No signal, radio turns itself right up. So when you tune off the signal, you hear this roar and this hiss. Now that roar and hiss is loud coming out of the speaker because essentially the volume has been turned to maximum automatically. That's why you hear it. If you turn off the automatic volume control, and a lot of high-end sort of communications receivers, you can certainly do that. Then when you tune off the station, instead of hearing this huge roaring hiss, you hear almost silence, maybe a faint hiss, because the radio is not automatically cranking up its volume. Now, the reason I'm explaining all this is because it'll help you understand the sound that we're hearing coming out of the speaker. In some cases, that sound would literally be put, 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 put. It would sound like that. In the case of this radio, I believe what we're hearing is the put, put going really fast. So it ends up sounding more like a kind of sound. Sorry for my imitations, but that's the best I can do. What's happening here is, let's just start with a strong signal. Strong signal comes through. Radio says strong signal, got to turn down the input. It begins to turn down the input, but it's delayed by this capacitor. It takes time for this capacitor to do its thing, fill up with charge basically. During that time, loud signal coming out. Pup, 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 pup. Actually, it would be a puh. It'd be the puh part. Eventually, this capacitor charges up, and the radio turns down the output. The output goes down. Now you get past the puh, and you're into the part. Well, now it's turned down, so there's no signal coming out. So it begins turning it back up again. As it turns it back up again, you start hearing more of the put sound, and then it goes down again, and up again, and up and down, and put, 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 and that's what it is, because of the delay due to this capacitor. We could call this the AVC capacitor. Let's look and see if they have a name for it. C13, so it's a large one. That's what I expected. 0.1, and there's no special name for it. This is the part number here. It's just C13.1, 400 volt, because it's on the screen circuits and they have a high voltage on them. In fact, that looks like the voltage written there, 80. That doesn't sound very high. This one's also fairly low, 90. And the plate, 205. 205. Notice the plate voltage in this tube is very low, 60. They keep the voltage low on the plate on the detector tube for reasons I don't fully understand, but I think it has to do with noise generation. I'm not sure of that. And this is the capacitors I was questioning when I started the video. The two yellowy green capacitors. I was saying they may be fairly new, they may be quite old in fact, they may be working fine, they may not be working fine, I'm really not sure. This is how they're shown on the schematic. Of course, in the radio now are separate capacitors. You can see them, they are separate. Originally, there would have been one 3-part capacitor, and that's why it's drawn this way. It's one device, but it's really 3 things inside it. So they've been separated out. Now, two of them in the radio by somebody previous to me. Now, 2 of these are probably, one of these is probably a bypass. So let's just find that out. So we're looking here, we're looking for a bypass on the cathode. So we're trying to follow the cathode connection. Here it is. This is the cathode. This is the cathode connection here. And these pins are numbered backwards. These pins are numbered as if you're viewing it from the top. That's unusual. They almost always number these as if you're viewing it from the bottom, because that's usually what's happening. Somebody's looking underneath. Of course, you know, it's like a clock. You turn it up, turn it, like you look at the back of a clock and the numbering is backwards. You've probably never looked at the back of a clock. Okay, so so coming down off of here, we find a resistor. This is probably a 200 or 300 ohm resistor. Let's take a look. R10. Oh, that's C10. Oh, yeah, R10. R10. 510 ohms, 0.1 watts. So 510 ohms. So the job of this guy is to cause the cathode to run a little bit positive relative to ground. And when it does, it becomes positive to the grid. Or you could say the grid is negative to the cathode, which is the way all these tubes operate. The grid is held negative relative to the cathode. That's how they control themselves. So, but rather than force the grid negative, you can force the cathode positive and get the same effect. And that's what's happened here. So this is called cathode bias. A 500 ohm resistor with the tube current flowing through it probably produce 5, 6, 7, 8 volts here or something like that. So usually this is bypassed. Now there's usually a capacitor going to ground. So we just follow this line and there it is. So one of these three sections is a bypass capacitor bypassing the cathode resistor of the output tube. Its value is going to be, well, I don't know, can you read that? I can't read that. I don't know what it says there. But it you know what? It's probably down here. It's probably in the capacitor list. Maybe not. Oh, here we are. It's in the here it is. The three is C19 and a 3-part capacitor. 12, 12, and 16 at 50 volts. 16 at 50 volts is the one that's doing the bypass. 16, and these other two are probably not very big. 12 and 12. So often in radios you're looking at 50, 75 microfarads in the filter. Here you've only got 12, and the reason for that is the field coil, this coil right here in the speaker. This is part of the power supply. The way they've drawn it, it's hard to see, but in fact, if you come to the top of this capacitor, you go through this coil, and you reach the top of the other capacitor. So this is two capacitors here, and this make a pi filter, and this is a very powerful filter system. You don't need a lot of capacitance to make it operate. In fact, in most of these radios, my experience is, even with these original capacitors, if it had the original ones in it and they weren't working very well, you still get a hum-free radio just from this big coil. So very impressive, but expensive, you know, big coil like that. With modern radios, they don't do it this way anymore. You've got a cheaper approach. Bigger capacitors, the coil becomes a resistor. That's kind of how you cheapen it all out. Okay, so we've discovered cathode bias, bypass capacitor. These capacitors should be small. We'll look in the radio in a minute and see what they actually are. And if these capacitors are weak, we still get a fairly hum-free radio. That's been my experience, as I just repeated myself to make sure I heard me. Now, what other interesting things can we find here? Tone control. The tone control is through this capacitor, and all it's doing is it's robbing the high frequencies at this point and throwing them away into the chassis. So it's a high frequency cut type tone control, which is extremely common. Done on the grid circuit of the output tube. But you can do this in a couple of different places. If we look at the volume control now, is there anything unusual going on here? This is the volume control. It's hard to see, but this part here, there's a little arrow right there. And this is the part when you turn the volume control, this part, you know, is sliding up and down here on this resistor. You're picking off more or less of the signal in the resistor here. No, there's no. It's a very straightforward thing. There's no tap on it. There's no positive feedback coming back. There's no tone controlling going on in here. Very good. C14, I'm just interested in what the size of that one is. C14, 500 picofarad mica. Okay, it's a mica capacitor is what I thought. Okay, that's good. That's good enough for now. Down the road, I will go through this and explain stage by stage how the whole thing works. But for now, I'm just trying to fill my head with the points that I need so I can make the right decisions and going forward. We need to find C13, replace it, and watch the motorboating go away. That would be my hypothesis. C14, there's no diagram showing where the parts are, so we just got to hunt it down. It should be fairly large, but because it's on a circuit that runs through tubes, the capacitor could be almost anywhere in that chassis. And is there any other 0.1s? So if there's only 1.1, we know there's a 0.2, 200 volt. Where's that? 0.2, and that's it. Yeah, so this is the only really big one apart from this one. C12. Oh, don't worry about it. Okay, let's go looking for it. Can we find it? So these are the two capacitors that are in the power supply that have the field coil on the speaker. The field coil's here. Field coil on the speaker in between them, and they form the power supply. In fact, see the wire here heading to the speaker? It's heading to there's 4 wires in here. 2 of them are heading to the field coil. And you could guess, I'm going to stick my fingers in there, it's these two. These two put the capacitors. So you see, capacitor, coil, capacitor. Pi, right there, you can see it right there. Pi filter. Oh, I'm too excited this morning. I don't know what it is. Yeah, a really good night's sleep or something. And I forgot what it was. What were we going to do? Well, now would be a good time to have a little bit of coffee. Got to change this guy and test them out, but got to make sure this one is good. Oh yeah, I know what I was going to say. So 1, 2, there's 3. It's a 3-part original. The original capacitor was a 3-part guy. Here's the 3 parts. Now discrete components. This one here is a 150 volt 20. And what did it say on the schematic for the bypass? I think it was bigger than that. I'll just peek on my own here. The bypass was 16. Okay, so it's supposed to be 16. Put a 20 in, putting a bigger one in, not a problem. He's used an electrolytic one here, probably not a problem. That's same as the original. These guys are, this is a 10 at 500 volts. So it's certainly got enough voltage. But 10, it's supposed to be 12 or something. And this one is also 10. So he's put 2 10s in it. This one's at 450. Got the right voltage, a little bit small. Probably not a problem. I think I'm going to leave them for now. They aren't an issue at this point, that's for sure. Do this one for safety's sake. Now, where's that big honking point 1? Could be this thing. Can you even see it? You wouldn't even know there's a capacitor there. It just looks like dirt. And there's a big one that's in terrible shape under here. Let's take a closer look at those two. I think we're going to see the 0.1 value on one of them here. Okay, so yeah, let's try this one first. Wow, I've got the automatic focus on. And I'm going to have to stop for a second. I'm going to stop, have a coffee, fix the focus on this camera, and then we're going to carry on. See if we can identify which one of those two is the 0.1. We'll change the 0.1 that we think is the in charge of quieting the. I can't talk while I do this. I'm breaking down. There we go. Whatever I was going to say, You can finish it. I'm going to go for a coffee and then we're going to do the work here. Okay, so I've installed a new chassis that runs between the power cord, a new chassis. I've installed a new capacitor that runs between the chassis and the power cord here. And here's the old one, but now I'd like to know what condition this was in. So we're going to put it on a test set over here. Okay, that was a bit of a rough ride getting over here. Now, my clip lead here is just about to break. I think it's down to one strand of wire. So, I mean, I get away with this without having to do a little house repair. Let's see. So what's happening here is I have the capacitor connected to this device. This device does a couple things, but one of the things it does is it'll put a high voltage onto, well, these are all the old capacitors from my last project here. Let me get these out of here. I get things mixed up. I have too much stuff. Okay. So it'll measure the capacitance of a device like this, a capacitor. It'll also apply a high voltage to it and then indicate whether there's current flowing through it. High DC voltage. A good capacitor like this, you could put 500 volts across it and it'd be basically zero current going through it. 500 volts DC. There's a charging current that flows in. Once the capacitor is full, nothing more goes in, just like a pail of water once it's full. So, just making sure of things. So when I hit this switch, it'll apply the voltage. I control the voltage with this setting. We start with a low one and work our way up. Now there's no meter here to indicate it's this. It's the magic eye. You can see at the bottom of the magic eye is not lit. There's like a pie shape that's open here. When current flows into the capacitor, the eye closes. So a good charged up capacitor after the initial charge should look more or less like this again. Back to no current. There's no current flowing right now, so the eye is open. So when I hit the switch, you'll see the eye snap closed and then open again to some degree. It may not open at all, or it may open right up. Here we go. 50 volts, what do you say? Okay, so it's opened up about half. So as these capacitors go, this is not the worst guy in town, but he's not in very good shape. Would this leak enough electricity to give somebody a shock? I don't know. That's a loaded question. I don't know. But I know this, the one I put in there is going to leak nothing. And that's a special capacitor, this one here. It's designed to be in these kinds of positions, basically across the power line or something like that. They're not likely to fail into a fire. And I think that's the basic message with those. The rest of these, they could start a little fire, maybe. Possibly. I guess if you're a manufacturer and you're going to make 10,000 of these radios, you start thinking, wow, 1 in 10,000 catches fire? Hey, that's possible. 1 in 10,000 catching fire? That's possible. Burn down one house and your radio's blamed, you're out of business. So you better take steps to make sure that even at the rate of 1 in 10,000 radios, they're not burning people's houses down. And I'm sure it happened. I'm sure it happened, especially in the early days when the electric system itself was not well protected. The fuses in your house weren't all that good, if you even had a fuse in the earliest days. So anyway, okay, now what? No need to operate the radio yet. That's right, we were going to go after the two capacitors and try to figure out which one is the .1. So we're looking on this waxy beast here. See the cracks in the wiring? All the red wire looks like that. So leave it alone, you're probably okay. Bend it in the slightest and chunks of insulation are going to pop off and you're going to have a bare wire, which in itself isn't necessarily a problem, but could easily be if if the two wires are in contact, like see those two crossing each other, the two red ones, see the cracks? See, if I'm not, I could be fiddling around way over here doing something. Meanwhile, I've shook the insulation off over here and the two wires are now in contact. It can happen. And look, now this is one of the resistors that was getting a little warm. Doesn't look very good, does it? Could be somewhere in its history it took a beating. It's no longer taking a beating. It's possible. There's a history of these things. This is the one that was getting quite warm. 50, 60 degrees. It's probably just fine. Of course, you see that its cousin, the capacitor here, is being roasted by this resistor. So this isn't really the best arrangement, but I guess it's the best they could do in the design of the radio. But these should have this, just even, see this very end here, you just move that, just, you know, millimeters, you make a difference in how hot this capacitor is getting from the resistor. Is it really a concern? Probably not. Once again, my mouth keeps opening, words keep coming out. Having an easy time talking today. Okay, back to what we're looking for. So this could be the guy. Let's see, one end is connected to a spot where a bunch of other stuff is connected. That could be a grounded terminal there. It's popular. A lot of wires and resistors, everybody loves it. What's on the other end? The other end is going to a tube pin. So, and there's a capacitor right on it. This mica capacitor here. So you could probably identify that pretty easily. Chicago. Hey, the tube socket was made in Chicago. That's when the United States was a manufacturer to the world. Seems like countries take turns doing that. Okay. I can't see the size on here. Now there's another one right here. Can we? Ooh, 0.006. So that's not a 0.1. So all the fluffy stuff on the end there, that's all beeswax. For some reason, that's collected down there. Don't know why exactly. 1,000 volts. Oh, I think I know what this guy's doing. I think he might be across the 1,000 volt. I don't have a 1,000 volt capacitor. Wow. I think it's involved with the output transformer. I think. So yeah, getting back to what I'm doing. I'm just seeing so many interesting things here. I'm getting thrown off. So 1,000 volt, 0.006. Well, that's not it. There's got to be a 0.1. Where I'm just going to go hunting here. Maybe it's up where I can't see it. Oh, what's that? What's that in the back there? You know what? This is in a position I have not seen it with my eyeballs. Oh my God! Is there two of them in there? Oh, this is a really awkward spot. There's two of them tucked up in there, and one of them looks pretty big. I get more light on this. It's just tucked up in a spot that, as I stand here in front of the radio, my eyes don't see it. So I haven't seen these two guys up here. 400 volt capacitance. It's just out of view. They could rotate that. I could read it. But this is the upper capacitor there. Type. So one's 400 volts. Wasn't that the case? One was a 0.1 400 volts, and the other was a 0.1 200 volts, and they're hooked up. Well, that's a ground. So they're both grounded at that end, and the business end. They are both connecting to this tube. Wait a minute, this one is coming around the back here, connecting to the tube. What tube is that? That is this tube. Come on, who's on my, standing on my camera wire here. Which one's this? 6A8. So, okay. 6A8. This is the very front end of the radio. So these two capacitors hooked up to the 6A8. Or so it appears, because sometimes a terminal on these radios, on the tubes, are not used for the tube. Sometimes the tube doesn't even have a pin to go into the terminal. Yet the radio designer will use the terminal as a connection point. It's just a free connection point. And it makes examining the radio very difficult. There's the ground. Solder job. Well, that's interesting. Wait a minute. So if this... Oh, see the black from the capacitor there. The black wire wraps around. Comes past the grounded terminal to the one with the two resistors and the red wire. And over to this terminal, which is tied to that terminal. Yikes. Okay, I just can't look at this and figure it out. Two terminals on this, on the 6A8. Let's look at the schematic. Okay, 6A8 is the first tube, and you know, so here's one of the capacitors I'm looking for, and they show it pictorially close to this tube. And how much I want to bet C12? C12 is the 0.2, 200. And it is connected, they're connected to, well, here on the schematic, they appear to be connected together and connected to ground. And that's exactly what we see in the radio. And the other end, see on the schematic, it goes on these wires. So one of them goes straight to a pin on a tube and nothing more, or not nothing more, or yeah, it goes into these coils. And the other one connects to a spot where there's two resistors, and that's what we saw. So I think we know. I think we know C12 and C13. C13 is the one I'm interested in right now. C12, what is it doing? What's it doing in here? Yeah, I'm not going to be able to sort that. Oh no. No, they have nothing to do with each other. They're just sharing a common grounding point in the radio and on the schematic here. So I don't know what this guy's doing offhand. Looks like it could be bypass of R2. R2 could be cathode resistor, R2, 220 ohms. Okay, R2 is a cathode resistor, and C12 is a bypass. So the C12 not important in the operation of the radio. C13 extremely important. This is the motorboat killer, the motorboat maker. He makes the boats, he crashes the boats. 0.1, 400. I'm going to cut the one out of there that says 400 on it, and I think we'll see the 0.1. And we're going to check it. Okay, back to the radio here. Okay, now you can kind of see the problem is these capacitors are way up in behind here, and nothing's easy about that. So when I cut the capacitors out, what I do, you notice, see how short the lead is here? I'm trying to leave as much wire back in the radio, and the wire can be helpful in connecting the replacement part, as opposed to trying to go right on the terminal, which can be quite a challenge in many cases. You know what, I gotta get down on my knees here to see the right angle. Okay, can you easily see what's going on? Easy does it. So we're gonna clip this wire. Now, at this point, it's real easy, not just to clip the wrong wire, but to clip 2 or 3 wires at once without realizing it. I think I only did one. Get the back side of this guy here. If I can get in there. I have to get a soldering iron in here too. This is wanting to go through here. Oh my gosh. Oh, wow. Okay, that's not going well. tip this radio back a little bit this way. Okay. Now reach right in there and cut that wire. How about this? The spring is gone. Oh, and all my excitement here, I'm going to cut the wrong wire. Get in there and go, yay! And I cut the wrong wire. Let's cut the right wire. Something's going to get cut. Something got cut. What did you cut, Jen? I think I got the right thing. Yeah, he's on the move. Come on out. Come on out to see the daylight. You've been hidden back here, living your life, hidden away. Nobody even knew about you. Come on out. Here he comes. Here he is. We got him. 0.1, 400 volt. Bingo! We got the right guy. Let's test this guy. So this is the guy I think is the problem. Is the reason why we've got the motorboating. Not sure. Can't be sure. Okay. I'm cutting the leads, trying to leave as much of the lead back in the radio as possible. Which later I may cut away. You know, further efforts or whatever may cut it away. That I leave enough on here to do this test. Enough wire here. $50 volts. Watching the eye. Closed right up. Not coming open. Quite a leaky capacitor. Now we I'd like to test the capacitance, but that's kind of a non thing. Once the capacitor is leaking like this, you can't measure the capacity. My capacitance measurements are off, and it's a capacitor with a big resistor in parallel with it. Now it's not quite the same thing anymore. The big resistor is its own leak. And think of it as a resistor. So I got to get a new one in there, a new 0.1, and it's got to be high voltage. It's got to be a 450 or something like that. Okay, I'm going to attend to that. Hey, I'm going to drink some coffee too. And then we're going to operate the radio and see if the putt-putt went away. Luckily, I'm able to prop the radio up in a very favorable way because I'm working right up in the back corner here. And I got two capacitors here. I'm going to replace both the ones that are up here because if I'm up working in this area, I might as well do the other one too. The other one is a bypass capacitor. It's sustaining 10, 20 volts, something like that. It's not much at all. For that one, I'm going to use a 400 volt capacitor on the counter. That's what I got. The other capacitor, I'm going to use a 600 volt capacitor. It's going to sustain B plus or close to it. So what I'm going to do is I'm going to put these guys together kind of the way they were in the radio. I'm going to twist one lead around the other like this. And I'm going to solder that, cut this tail off, and then the two capacitors have one lead to ground, and then the other two leads will attach to where they need to go. That's what I'm going to do. Well, it's a little bit challenging getting that one out. Let me just knock down the light level here a little bit in the shop. Yeah, it's very awkward trying to get a cutter down in there to cut the wire. Here he comes. So this is the bypass capacitor. It feels heavy. Feels unusually heavy. Capacity is 0.2 right there. Good, so I'm putting in a 0.22 in its place. Let's give this guy a test. Looks to be in pretty good shape. So I'm looking at the end where the wax seal around the wire here. Of course it gets roughed up when I remove it, but sometimes you can look at that and you can just see it's gapped out, and that's going to let the moisture come in. The purpose of the wax on here is to stop moisture from penetrating into the capacitor. That's why it's waxed up. Alright, okay, I'm going to attach it. My clip lead's still hanging on. Come on. Just a little strand of wire there. Okay, 25 volts. Watching the eye. What do you see? I'm trying to cast my shadow on it there. Here we go. Oh, it's just, the camera doesn't do justice here. With my eyes, I can see that the pi there's a tiny little gap in it, but it should be popping right open like that, and I should be able to go right up to the rating of the capacitor, and every time I hit that switch, opens right up, but it doesn't. So regardless of how it looks, it's also, I assume, it's moisture that's doing it. Now I'm going to do a silly test here. I don't want to say too much about this, but I'm a curious person. I like to check things. I like to see for myself what is going on. So I'm putting this on to DC volts, and you can't even see what I'm doing over here. Come on over here. This is where the excitement is now. So I have this on very sensitive DC volts. Just making sure it goes to 0. Now I'm going to connect to this. Oh, I don't want to be touching it. Whoops. Okay, didn't think this through 100%, but here we go. I'm going to clip lead the battery. I don't want to be touching the leads when I do this little experiment here. So this capacitor has been laying around on my bench. I did test it with high voltage some time ago, but surely to goodness, with an internal leak like what it has, whatever voltage was there is gone. Now watch the meter very carefully when I make the connection. Something may happen very quick. Here we go. Well, it's not quick. It's happening slowly. What's going on? Okay, well, it's just charge left in the capacitor, right? And I'm just bleeding the rest of it down. So there's a voltage here of 162 millivolts. So that's one it's a small voltage. It's going down. Now, if this is residual charge, then I should be able to let this go, and the charge should just sit there. And when I connect again, we should see the very same number we saw at the end. But you see it's higher? It was 180. Watch again, okay? So we're at the 160, say 160. Now we're going to connect. Watch carefully. Whoops, I shouldn't have done that. We had to make a very good connection immediately. 180, 170, 160. What happened? How did it get voltage back into it? But you might say, well, okay, so the electrical energy is soaked into the dielectric and you're just bleeding it out. No, I don't think that's what's going on here, because if I leave this connected, and I'm gonna leave this connected here, it will go down to a certain voltage and then stop and just sit there. It may take a while. So I'm going to leave that just doing its thing while we get back looking at the radio. I haven't explained what that's all about yet, because I have found in the past sometimes if I make an explanation and then do the demonstration proves the explanation was wrong. So now I like to do the demonstration, see the result, then I can make up an explanation to fit the results, like a scientist. No, that's not science. That's definitely not science. Okay, so I'm going to install these two guys, and we will look at our capacitor experiment after that's done. The voltage right now is 148, barely going down. Okay, 2 new capacitors are in. Let me just check. So I'm just checking to see that they're rigid, you know, from good soldering. As rigid as they can be. Good. So we did that. We did these 2. This guy making it a little safer than it was. And these 2, one of those 2, making it work again, I think. Oh, I left a couple of capacitors in my tray. So let's clean up just a little bit here because we're going to power this up. And I don't like doing that with a big crowded bench here, tools and stuff. And the reason is, if a panic ensues, the last thing you want to look at is a complex bench full of stuff while you try to find something among the stuff. It's better to kind of, go back to the starting line, put everything where it's supposed to be. Oh, our experiment. Yes. What about that capacitor experiment? Now my meter went to sleep here, so I don't know what kind of influence that would have on it. Probably a big influence. Yeah, it's starting over. That's what's happening here. So it's 0.2 volts. I mean, that alone should be enough to prove what I'm about to say. That this capacitor is turned into a battery. It's got enough mixed metals in it and enough moisture in it that the 2 different kinds of metals are now reacting. Probably the lead metal, which is plated steel, I think. Some kind of like a nickel-coated steel or something like that. I don't know what. And the other material would probably be aluminum foil inside. So aluminum is pretty high on the EMF scale, and that's enough to cause this. So now you see it's stable at this. This is the power of the battery, matching against the meter. The meter's drawing some power, a little wee bit, out of that. If it's just a capacitor here, then this would just keep falling all the way down to 0. But it's not. So there you are. So these old capacitors get moisture in them. They start developing their own voltage. Now, there's not much oomph behind them. I mean, you're not going to put a bunch of these in your Tesla and drive around. That's not going to happen. But does that have a bearing on the operation of the radio? In certain spots, could it be a little bit of voltage generated by the capacitor itself throws the radio off? I'm not sure. I'm not sure if that's important at all. Never read about it, never heard anything about it. I think that's my little idea there. I'm the owner of that. Capacitors become batteries in old age. So I'm going to take a little break, and we're going to set this guy up to operate and see if we haven't knocked out the problem. Not too often we get a normal look at this radio. It's been upside down and sideways the whole time on my bench. Look at this terrible stuff that's going on here. So there's some kind of coating which may exist over the whole thing, and it's peeling off here because of corrosion crawling up from the bottom edge. Edges are very hard to protect. That's why your car tends to rust wherever there's a sharp edge. So if you look at the bottom of your doors, I mean, automakers have been working on this for a long time, so maybe they don't do this anymore, but your door is made of an inside piece and an outside piece of sheet metal. It comes down and it joins at the bottom. And what they do at the bottom is they put it together, and it's hard for me to show this with my hands, but they fold it up, maybe fold it up twice, then they press it. And in there is a sharp edge, the sharp edge of the metal. And they try to coat that and cover it and get that sharp edge out of there, because you can't paint a sharp edge. You cannot. The paint film on a sharp edge is so thin as to not be there. So you may put enough coating on the main piece of metal and it'll never rust, but this edge, it's bad news. There you go. Why am I telling you about this? I don't even know. Okay. So not plugged in yet. Practicing. Okay, so that's probably the broadcast band. Oh my God. I really Oh, it's okay. Can you see that? It's okay. Good. Okay from Mr. I don't know what number that is. They should have signed their actual names. A long time ago when I was a kid, I saw something on TV and the suggestion was everybody should be forced to sign their work all the time. And the example they showed was a guy painting the line on the middle of a road, and when he got done, he's signing his name on the road, that he's the one who painted the line. If people sign their names to their work would be a lot better, for sure. Hey, you know what? I'm going to take that a little bit further. Too bad the internet developed with people being allowed to use nicknames. I personally think everything you post on the internet should have your real name on it. And if you don't want your real name on it, then you shouldn't be posting it. But because people can hide behind character names, it's freed them up to be bad actors, because they're hiding behind these crazy character names. Tell you what else I think of the internet. Did you know the internet existed when I was in high school? I was in high school in the 70s. Where was the internet located? Well, I discovered it in the boys' room. You sit down on the toilet and you look at the wall beside you, and there's the internet. Right there. People making comments. Nobody knows who's doing it. People feel protected while they're writing on the wall. Yeah. To a large degree, what you read on the internet is the same crap we read on washroom stall walls. There you go. Now, stop speeching, Jim, and let's get this thing going. Shame on me for delaying the exciting moment. So, without a doubt, I will be utilizing the lights. Now, both of these are screwed in, and we're ready to go here. Here we go. What will happen? Is it switched on? Switched on? No, not switched on, but that's okay. Testing. Testing 1, 2, 3, 4. 119 volts, a little extra. That's because I fiddled with this earlier. I'm just going to knock it back a little bit. So full power will be 115 volts or thereabouts. But we're going to run it through the... here we go. Power on. Okay, we got to watch the lights. What do they do? Oh, it barely came on. I don't like that. I expect it to come on pretty bright. Now see it brightening up? Can you see that? So that'll be the tube starting to warm up. We should hear something out of the speaker now. Where's the thump, 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 thump? It's coming. I fiddled with the switch. I may have switched it off radio onto phono without knowing it. Let's turn it up. Let's try the switch. Not too exciting yet. Okay, band switch. Band switch. Volume. Or is this tone? This is volume. No, this is volume. I don't know. One of them is. Oh. Ooh, I like that sound. We are doing this without an antenna. I like it because there's something coming out of the speaker when I'm doing something with the radio. I like that. I mean, it's not the best sound. We need to put an antenna on it. But first, I'm going to inject signals. I am going to be the injector of the signals here. So what I'm going to do is I'm going to touch these caps with my finger, and we're going to see what comes out of the speaker. Now let me just turn this down a little bit. Turn it up. Thumbs up. That's good. Oh, 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 oh. We should hear that. We're not hearing it. I can't really touch in there. They've got that covered up so good there. I can touch it with a screwdriver. Can't really get a shock doing this. Get ready for noise though. Not quite what I expect. I have my finger on the shaft here, so I should... Big noise here. So the radio signal progresses this way. It's coming around, going like that. So first tube, second tube, third tube. Third tube is connected to the speaker. These ones, not so much. Why? We can guess. A defective tube, that's a good guess. Other problems underneath the chassis, lack of B+ being applied to the tubes, all kinds of things could be causing this. So I'm while the radio's operating, oh, you know what else? Hey, too low a voltage. Yeah, that could be it. Just too low a voltage. Okay, volume down. We're going to give it the full Monty here. If anything's ready to go, it's going to go now. It's 111 big volts on there. Let's turn it up. Ooh, that's interesting. Okay, that sounds like the record player with no record player. That sounds like a radio. Let's tune this baby. Ooh. So the volume's up pretty high here. So that scratching is not a serious problem. Here we go. This radio's operating now, I think. Oh, that's loud. Very loud. Maybe I can tone it down. That's a little better. Something really scratchy in the tuning. Okay, so I think I'm on the shortwave band. Let's go to the broadcast band. Things got kind of quiet. Okay, now the antenna is this wire back here, this piece of wire here. Let's give it the antenna test. Hear the difference? Notice I'm only touching one thing at a time with my hands, by the way. I think it's working. And we go to the short wave. Dirty switch. There we are. Let's go back again. The switch here. Switch a problem. Okay, what we're going to do now is we're going to hook up a proper antenna to this radio and we're going to play it. We're going to see what it does. Good show. I have to set that up though. Okay, so what's happening now is I'm going to hook up a very good, what I've concluded is a very good outdoor antenna. So the antenna comes with two leads. The red one is the center lead and the black one, of course, is the ground. I'm just going to hook up the center lead to start with. And I turn the volume down. What can you pick up, Mr. Radio? Switch needs cleaning. There we are though. So we're tuned to somewhere. Oh, this is reversed. Like the low numbers on the right. Okay, so we should be over in this area if we want to pick up stations. Oh, what happened? Where'd you go? What happened? Band switch. Something just happened. What happened? Come back, radio. Where'd you go? It was working and then it was not. I don't like that. Hello, radio. Band switch.
In business with Mike Apple. It's 10:55. If you're planning on replacing your windows,
I'm not. This is probably 680 here. Now I'm going to take the free ground lead and I'm going to ground it onto the ground wire. This long clip lead, which I think probably somebody confused this with the antenna. Does it get better or worse? Better. So this is the performance of this radio now with a good, strong antenna on it.
Certainly that's a factor that will lengthen the notice period, the severance that you're entitled to. I'm finding
probably
that
640.
more and more
Probably 610 from St. Catharines. That's on the far side of Lake Ontario from here. It's a long ways away.
Weight classes like my dad.
This will be 590.
When I was growing up, so I've been following for a long time.
Okay, now
I just love it.
we're going to turn this down. We're going to switch bands. Can you pick up any short wave with this guy? Same antenna will do it. Oh, got to turn the volume way up. So we're at 6 megahertz. Really, short wave stations are going to be up in this area at this time of day, up here. Band switch acting up again. Dirt in the tuning capacitor. Okay, anywhere up here. You heard the station there. It's just blaring. Very strange. Ooh! What was that? So I think it's the tuning capacitor. It has some dirt on it. And if I could just find a clean spot. Give me a clean spot. Let's attend to that a little bit. Just need a stick. So what we're going to do here, rotate this very carefully. I think it's this guy here. Let's see. Maybe not, because it should be popping and making sounds there. Gotta get it to No, I think it's something else. Something very odd. So now it sounds more normal. You hear the atmospheric hiss. You have to excuse me, I like tuning radios a lot, so we're going to go up around 15 here. Ooh, more of that.
WCR, our website not only offers you a way to listen to WCR online, but also gives you a transmitter and program schedule. Whether you listen online at wwcr.com or on shortwave, we thank you for tuning in to Worldwide Christian Radio, WWCR, Nashville, Tennessee, USA.
Good evening, friends. Tonight's program on your firm foundation is a...
Good evening. It's a recording, that's why you said good evening. Okay, well, so that's a pretty darn good showing at this point already. Great thing is, let's switch it off now. The radio largely operates. So from here on, as I make changes, I can test the radio, and if I've done something dumb, I should be able to figure that out right away, because the radio won't work properly. And so then I can correct my dumbness. Until the radio's working like this, every time you make an improvement, it might be the opposite. You might be making a mistake or something of that sort, and you can't tell. And this, if you travel down that dark road, you'll end up at a place you can never get the lights on again. You just potentially make enough mistakes that you just can't sort it out without doing some kind of heroic effort of examining every wire and every little part and all that kind of stuff. So that's why I'm so excited this is working. It also says, hey, this radio works. Now we know. There's no doubt about it. It's just a question of improving its performance now. And very good. Very good. We'll cut the power there, Jim. Cut the power. Very good. So thanks a lot for watching. I think this is probably a long video, but we had to get to this spot here. So from here on in, it's out with the old capacitors and continuing improvement in the radio's operation. Eventually alignment and bingo. Great. See ya.